Hello everyone, this is Group 13 and our topic is portfolio optimization based on maximum acceptable risk. Our table of context is as follows. When investing in stocks, one way of minimizing risk is to compose a portfolio consisting of multiple stocks. We naturally want to maximize profit while minimizing risk, but this cannot be achieved by an analytical approach, since there is no governing equation regarding risk and expected return of stocks. Therefore, numerical analysis is needed. For numerical analysis, we define the risk of portfolio as the under red line. The expected return of portfolio is evaluated by multiplying the stock ratio vector omega and the stock expected rate of return vector mu. Our project's objective is to find out how omega and the expected returns change as the given acceptable risk value changes, satisfying two constraints as shown. The first constraint explains that the sum of the proportion of assets should not exceed 1. The value was set to be equal or less than 1 because not using all assets within the allowable risk level could lead to greater returns. The second constraint explains that the risk should be smaller or same than the maximum risk level allowed by investors. First, we collected stock data from Yahoo Finance website. We chose the time period as shown, and we used the close price data for the stock value. And before deciding which type of stock to use, we chose 4 categories that seem not to be related to each other first. 11, 11, 12, 13 each. And as a result, we made a 47 by 2939 matrix as shown. And I'll explain why we chose the categories that seem not to be related, explaining about the term covariance. Covariance is a value that shows the correlation between two random variables. If the covariance is positive, it means that they tend to move in the same direction. And if the value is negative, they tend to move in an inverse direction. The formula of covariance is shown on the slide. When calculating covariance matrix, we use the fluctuation of the stock price rather than the stock price itself. This is because if we use stock price as the data, covariance value will differ a lot depending on the stock price. For example, if you see that you can see that the covariance value of matrix A and B is 0.25 and the covariance value of matrix A and C is 250. But you can see that the stock price matrix AB and AC have the same rate of change, but the covariance value is 10,000 times different. To use the fluctuation as the input data, we divided the stock price data into 10-day intervals and we used the average 10-day rate of change as one data. And the calculation of covariance is done by 2 ways. The first method is using the MATLAB built-in function cov, which uses the arithmetic mean. But we used a second method, which uses the geometric mean to get a more accurate result. And we normalized the covariance value, which is called the correlation coefficient, and we visualized the correlation coefficient value using the function heat map, as shown. The stock data we have used have 4 categories. And we can expect that the covariance between the stocks of the same category will be higher than the covariance between stocks of different categories. And as you can see, the colors of the boxed area are slightly darker than other regions. And this is why we chose 4 categories that are not related to each other to see a meaningful result like this. Next, we calculated expected rate of return. Expected rate of return is the profit or loss that an investor anticipates on an investment. And we used 3 methods. The first method has a failure to reflect the tendency of the stock price graph by simply averaging past values. To overcome this error, we decided to use curve fitting method to estimate the expected rate. And these are the 2 results using 4th order polynomial and a linear function. And we can say that the red graph has a tendency of increasing, but the left graph using the fourth order polynomial is expecting the expected rate to decrease, but the linear function is expecting the rate to increase. So we made a conclusion that linear function is better at expecting the tendency. And this problem shows on many other examples too. And now let's move on to the optimization part. So far, we have calculated the expected rate of return and covariance matrix of each company. Now, using these values, let's find the proportion of assets that can yield the maximum return within the risk level used. To achieve this goal, we use the MATLAB optimization toolbox. Now let's look at the code. The optimization function can be divided into four parts: the part that generates the optimization problem, the part that generates the objective function, the part that generates the constraint, and the part that solves the problem. The following code is a code translation of what is inside the box on the right. And this graph is the result. The x-axis of the graph is the risk value, and the y-axis on the left is the profit, and the y-axis on the right is the variance of assets. And I'll explain why we added the variance of assets, explaining this red point. When the risk increased, the program does not distribute asset and just aim for biggest profit, which results to invest to only one company. And since we calculated the expected rate by curve fitting and linear function, the program will choose one company that has the biggest expected rate. And this kind of result cannot be called as a portfolio because the program does not distribute the asset. Therefore, we numerically calculated the distribution of asset ratio for each risk and plot the result in a red graph as shown. By seeing these two cases, case A is distributed well and case B is not. And case A variance is way smaller than case B. So we can say that small variance indicates that the stock is well distributed. Now let's move on. Now let's move back to the graph. The interpretation of the graph can be done by dividing the graph into three parts: the part where the sum of the ratio vector is less than 1, the middle part where variance of assets decreases and increases slightly, and the last part where the variance of assets increase extremely. The first part can be interpreted as the computer doing a passive investment. Since the acceptable risk is too small, the algorithm would rather keep part of its money as safekeeping. As the acceptable risk increases, it will put more money into the investment until the sum of the ratio vector becomes 1. The second part can be interpreted as doing a more aggressive investment. As the sum of assets hits 1, the variance decreases slightly. This may be because of the algorithm considering more dangerous options, which are stocks that have higher risk but also have higher potential return. As the type of stocks used in portfolio increases, the variance momently decreases before it increases again, due to the ratio focusing on stocks that have high return. The last part is when the algorithm starts to make extreme investments. As the acceptable risk become too high, the ratio of assets become focused on to only few stocks, those that have the highest expected return, regardless of their risk. Given enough risk, the portfolio will converge into a single stock that have the highest return. As a result, our group could make a deep interpretation about how the proportion of assets and the expected profits change depending on the maximum allowable risk. And this is the contribution of each member. Thank you for listening.